Good morning, everyone. So let's get started with the answer number two of this particular assignment for the CML661. So we were given a .cf file, zip file for the particular peroxide, which is barium titanium trioxide. This is a different crystal. Actually, no, not different crystal. Actually, it's a different way we have visualized. We have moved our origin. We have shifted our origin from this typical model, the default representation that we use in which as we can see that barium is at the origin and the titanium is at the body center and oxygen are at the phase center. But in this model which have been provided, we have shifted our origin from barium to the titanium and barium is now presented at the body center. So yeah, barium is present at the body center and the titanium is actually presented at the origin and oxygen is still the same. So this is the visualized structures using the Vesta software and we have to study the ferroelectric behavior of our this structure, the default representation that we have, in which this titanium is presented at the void that we have octahedral void. So the position of titanium atom in the unit cell is at the zero point 0.5 along the z-axis because we are, as you can see here, look here, as we can see, we have considered our this atom, barium atom at the origin and the position of titanium we have considered at the zero point 0.5, it is present at the body center. So it is our reference position. So this is zero point 0.5 unit along the positive z-axis and keeping the barium as the origin. And now we are applying electrical field once along the positive z direction. Then we are stopping. Then we are again applying electric field in the opposite direction, minus z direction. Then again stopping. And we are seeing how this particular peroxide behaves. We are actually monitoring this using this the position, the relative position of this titanium atom into the crystal system we have unit cell. So like is it staying at its place or is it moving upwards on the in the presence of light field or moving downwards? So this is what we have to visualize. So we have applied the electric field along CS is positive and negative and displacement of the titanium from its initial and the final position. So actually, this is the ZIF file. This is the ZIF that I have generated. I have generated totally 17 frames, starting with the structure number zero. This is our structure number zero, the default frame that we have used. And as we can see that this is structure number of frames that I have used, in which I have moved the position of barium titanium atom along the z-axis. That the initial it was 0.5 unit, then 0.75, 0.78, 0.8, 8.2, 8.1, 8, and so on. And if we see the relative distance from the reference, as we can see, reference is suppose it's always going to be 0, then 0.25, 0.28, 3, 3.2, it's like that. Then I have plotted this whole, oh, this is the remaining, the remaining entries or data about this ferroelectric hysteresis loop that we are going to get because of the barium titanium peroxide, it gets polarized in the presence of external magnetic field. So this is the hysteresis loop that we are getting for the barium titanium oxide. Barium titanium oxide. We're going to get similar to this, not this exactly, but yes. So we at the initial frame number zero, we have the titanium at the body center 0.5. Then if you apply the magnetic electric field along the positive z directions, then it is increasing like very rapidly. It comes to position 1, then 2 and 3, then 4, then it's going to saturate. And if you remove the electric field along the z direction, then it's going to slowly so it's remain magnetized, but it should be ideal case like magnetization. It's sorry, not magnetization, it's polarization. Electric electricalization should not reduce, should not decrease. But in the real life scenario, it's the electrical polarization decreases, and not to that much certain extent, but slowly. So from point number 5 to 7, we have removed the external electric field. And once it has come to point number 7, we are actually switching on the electric field from plus C to the minus C, we are switching. So from point number 8, it has finally dropped to the 9, and then 10, then 11, and 12. Again, it has hit the saturation. If we turn off the electric field, it is going to remain polarized till here. And if we are going to switch back the electric field into plus C direction, it is again going to go to the point number 1. It's going to run in loop from 1 to 2 to 3 to 4, then again 4, 5, 6, 7, and then 9, 10, 11, 12, 13, 14, 15, 16. It's going to keep on running like this. It's going to keep on running like this, like a hysteresis loop. So yeah, other than this, we were also given a few more structures for whom we have to get their zip file generated and then plot them. First is our calcium telluride, which has the rock salt structure. In the telluride Te, atoms are presented at the FCC, that is, they're presented at the, as you can see, these goldens are tellurium and they're presented at the corners and the face centers as well. And our metal are presented at the four octahedral voids. So it is actually CF4, Te4, and this is one of the calcium is present here, then other four are presented at the S centers. Because as we all know that the as is how 11 by 4th contribution, 12 atoms are there, and the three atoms are going to be there. So overall, if we're talking about this, calcium atoms are presented one at the body center, and the remaining three are presented at the 12 S's. Then we have gallium phosphide, which is zinc blende kind of structure. As we can see that the gallium is presented in the alternate tetrahedral voids, and the gallium, sorry, the phosphide actually it is presented in the FCC structure, as you can see on the corners and the face center as well. So totally it is also like CF4, P4 we have, and then we have A2O, which has antipolar structures in which the potassiums, eight potassiums are presented in the eight tetrahedral voids, and the four oxygens are presented in the FCC. As you can see, these red are the oxygen, these purplish are our K atoms. Then CEO2 have the fluoride structures, and in the fluoride structures, our oxygen atoms are presented into the tetrahedral voids, are 18 number in this case, and the cerium is presented on the FCC lattice. As you can see, these yellows are our cerium, and they are presented in the FCC, and we have eight oxygen atoms which are presented into the tetrahedral voids. And at last, we have gold zinc, which has a CSCl kind of primitive structures, in which the gold is presented at the body center of the primitive lattice, a primitive crystalline system, primitive lattice of the zinc, in which they are all presented at the corner, except the gold, which is presented at the body center. It is not BCC. For the BCC, this central the body atom also has to have to be Jadan only, but it is a bit different, so it is primitive type of crystal lattice. So this was the second answer these to this particular assignment. Thank you so much for being with me. Now we are going to move on to the next question as well.